Newton's law of universal gravitation. A late-night lecture in classical mechanics. Good evening. Tonight we will be covering Newton's law of universal gravitation. We will proceed through this material slowly, carefully, and with great attention to detail, as is appropriate for a topic of this magnitude and historical significance. There is no need to rush. The material will be presented in a thorough and methodical fashion, and we will revisit each concept several times to ensure that the ideas have been given sufficient time to settle into the mind, as sediment settles slowly and inevitably to the bottom of a very still body of water. Section 1. Historical and intellectual context. To understand Newton's law of universal gravitation, it is useful, indeed it is essential, to understand the intellectual and historical environment from which it emerged. The law did not appear fully formed from nothing. It was the product of decades of accumulated astronomical observation, mathematical development, and philosophical rethinking of the natural world. All of these things came together gradually and persistently in the 17th century. Isaac Newton was born on the 4th of January 1643 in Woolsthorpe by Colsterworth, in Lincolnshire, England. This date is given according to the Gregorian calendar, which was not yet in use in England at the time of Newton's birth, and so by the Julian calendar, which England was still using. The date was the 25th of December, 1642. This distinction is noted here not because it is of great physical significance, but because accuracy in all things, even in dates, is the proper disposition of the natural philosopher. Newton was born prematurely, and his early survival was itself considered unlikely by those around him. Newton was educated at the King's School in Grantham and later at Trinity College, Cambridge, beginning in 1661. It was during his time at Cambridge, and particularly during the years 1665 and 1666, that the university was forced to close due to the Great Plague of London. Newton retreated to his family home in Woolsthorpe, and it was during this period, this extended period of quiet, isolated, unhurried contemplation, that Newton began to develop many of the ideas that would eventually become his most important contributions to mathematics and natural philosophy. This period is sometimes referred to, somewhat dramatically, as Newton's Annus Mirabilis, or Year of Wonders, though in truth the work extended over a somewhat longer interval than a single year. The ideas that emerged during this time included the foundations of what Newton called the method of fluxions, which we now call differential calculus, his early work on the nature of light and color, and the early seeds of his thinking about gravitation and planetary motion. The famous story of the apple is not, strictly speaking, verified in the precise form in which it is most commonly told, but there is historical evidence that Newton did reflect on falling objects during this period, and that observations of ordinary terrestrial falling, combined with his astronomical thinking, contributed to the development of his gravitational theory. The story was recorded by William Stukeley, a friend of Newton's in his later years, who wrote that Newton had told him that the notion of gravity came to him while sitting in a garden and observing an apple fall from a tree, prompting the question of why the apple should fall perpendicularly toward the earth rather than sideways or upward. Before Newton's synthesis, several important pieces of the intellectual puzzle had already been assembled by other natural philosophers. Johannes Kepler, working in the early 17th century, had formulated his three laws of planetary motion based on the meticulous observational data of Tycho Brahe. Kepler's first law states that planets move in ellipses with the sun at one focus. Kepler's second law states that the line connecting a planet to the sun sweeps out equal areas in equal times. And Kepler's third law states that the square of the orbital period of a planet is proportional to the cube of this semi-major axis of its orbit. These laws were empirical. They described what the planets did without explaining why they did it. Newton would provide the why. Galileo Galilei had also contributed enormously to the understanding of terrestrial mechanics, establishing through experiment and reasoning that objects in free fall near the surface of the Earth accelerate uniformly, regardless of their mass, and that the distance fallen is proportional to the square of the elapsed time. These terrestrial observations about falling bodies would find their place in Newton's larger framework. Robert Hooke, Christopher Wren, and Edmund Halley had each been working on the problem of planetary orbits and had suspected, with varying degrees of mathematical rigor, that an inverse square law of attraction might explain the elliptical orbits that Kepler had described. Hooke, in particular, had corresponded with Newton on this matter. The question of proving, mathematically and rigorously, that an inverse square force law would produce elliptical orbits was the central, outstanding problem. It was Halley who, in 1684, visited Newton in Cambridge and learned that Newton had already solved this problem. Halley encouraged Newton to write up and publish his findings, and this encouragement led eventually to the publication in 1687 of the Philosophia Naturalis Principia Mathematica, commonly referred to simply as the Principia, which remains one of the most important scientific works ever produced. Section 2, the statement of the law, Newton's law of universal gravitation, is a statement about the force of gravitational attraction between any two objects that possess mass. It applies, as the word universal in the title implies, to all objects possessing mass everywhere in the universe at all times. This universality was itself a profound conceptual achievement, for it unified the physics of the heavens, the motion of planets and moons, with the physics of the earth, the fall of ordinary objects near the surface. The idea that the same force which pulls an apple toward the earth and also holds the moon in its orbit was not obvious, and its recognition by Newton represents one of the great conceptual unifications in the history of science. The law may be stated as follows: every particle of matter in the universe attracts every other particle of matter with a force that is directly proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. Let us say that again, in slightly different words, because the statement is worth hearing more than once. Any two masses, regardless of their size or composition, exert a mutually attractive gravitational force upon one another. The magnitude of this force increases as either mass increases and decreases as the distance between the masses increases. Specifically, the force decreases as the square of the distance increases, and once more, so that the essential content is firmly established. The gravitational force between two objects with mass is always attractive, always acts along the line connecting the two objects, and its magnitude is proportional to the product of the two masses, and inversely proportional to the square of the separation between them. Expressed mathematically, the law takes the following form. The magnitude of the gravitational force, which we will call F, is equal to g times m1 times m2 divided by r squared. That is, F equals g times m1 times m2, all divided by r squared. In this expression, F is the magnitude of the gravitational force in newtons, m1 is the mass of the first object in kilograms, m2 is the mass of the second object in kilograms, r is the distance between the centers of mass of the two objects in meters, and g is the universal gravitational constant. G is a constant of proportionality, a single number that sets the overall scale of gravitational force in the universe. Its value is approximately 6.674 times 10 to the negative 11 Newton meters squared per kilogram squared. Written more carefully, G is approximately equal to 6.674 times 10 to the power of negative 11 in units of Newton times meter squared divided by kilogram squared. This is a very small number. It is a very small number, and this smallness is the reason that gravitational attraction between ordinary human-scale objects, two people standing near one another, for instance, or two boulders resting on the earth, is utterly imperceptible only when at least one of the masses involved is of astronomical scale: the mass of the earth, the mass of the sun, the mass of the moon. Does gravity become a force of perceptible magnitude in everyday experience? The value of g was not measured in Newton's own time. Newton was unable to measure g directly because to do so requires measuring the gravitational force between two masses of known magnitude in a controlled laboratory setting, and the technology to do so with sufficient sensitivity did not exist in the 17th century. The first laboratory measurement of g was accomplished by Henry Cavendish in 1798, more than 100 years after Newton's Principia. Cavendish used a sensitive torsion balance apparatus in which small lead spheres were attracted to larger lead spheres, and the resulting rotation of a suspended rod was measured with great care. Cavendish himself described his experiment as weighing the Earth, because once g is known, and given the known value of gravitational acceleration at the Earth's surface, one can calculate the mass of the Earth. This was a remarkable achievement. Section 3. Vector form of the law. The expression F equals g times m1 times m2 divided by r squared gives only the magnitude of the gravitational force. To specify the force completely, including its direction, it is necessary to express the law in vector form. This is because force is a vector quantity. It has both magnitude and direction, and the direction of the gravitational force is always attractive, meaning that each mass is pulled toward the other. Let us define a position vector from mass m1 to mass m2. We will call this vector psi r, written with an arrow above it to indicate its vector nature, though in this spoken lectures we will simply say the vector r12, which points from mass 1 toward mass 2. The magnitude of this vector is r, the scalar distance between the two masses. We also define a unit vector in the direction from mass 1 toward mass 2. A unit vector has magnitude equal to 1 and carries only directional information. This unit vector, which we may call r hat 1, 2, points from mass 1 in the direction of mass 2. The gravitational force exerted on mass 2 by mass 1 is then given by the vector equation. The vector force on 2 due to 1 equals negative g times m1 times m2 divided by ar squared times r hat 1, 2. The negative sign is crucial. It indicates that the force on mass 2 due to mass 1 is directed opposite to the unit vector from mass 1 to mass 2. That is, the force pulls mass 2 back toward mass 1. Gravity is always attractive. There's no gravitational repulsion in Newtonian gravity. This is in contrast to electrostatics, where like charges repel and unlike charges attract. But gravity has no such duality. Every gravitational interaction is an attraction. By Newton's third law of motion, the force exerted on mass, 1 by mass 2, is equal in magnitude and opposite in direction to the force exerted on mass 2 by mass 1. This is consistent with the universality and symmetry of the gravitational interaction. Mass 1 pulls mass 2, and mass 2 pulls mass 1 with equal and opposite forces. Section 4. Derivation and connection to Kepler's laws. One of the great achievements of Newton's gravitational theory was its ability to derive Kepler's empirical laws of planetary motion from first principles. Let us consider how Newton's law connects to Kepler's third law, which states, as mentioned earlier, that the square of the orbital period is proportional to the cube of the semi-major axis of the orbit. For the sake of simplicity, let us consider a planet of mass m moving in a perfectly circular orbit of radius Acer around a star of mass m, where m is very much larger than m. We will idealize the orbit as circular, which is a good approximation for many planets in our solar system, since the eccentricities of most planetary orbits are quite small. For an object moving in a circle, there must be a net centripetal force directed toward the center of the circle. This centripetal force has magnitude equal to m times v squared, divided by r, where v is the orbital speed of the planet and r is the radius of the orbit. Alternatively, the centripetal acceleration has magnitude equal to 4 pi squared times r divided by t squared, where t is the orbital period, setting the gravitational force equal to the centripetal force needed to maintain circular motion, g times m divided by r squared equals m times 4p squared times r divided by t squared. The mass of the planet m appears on both sides and cancels. G times m divided by r squared equals 4p squared times r divided by t squared. Rearranging, t squared equals 4 pi squared times r cubed divided by g times m. This can be written as t squared equals the quantity 4 pi squared divided by g times m all times r cubed. The quantity 4 pi squared divided by g times m is a constant for a given central mass m. This means that t squared is proportional to r cubed, which is precisely Kepler's third law. The constant of proportionality is 4 pi squared divided by g times m, and Newton's law gives us an explicit formula for this constant in terms of the mass of the central body and the universal gravitational constant. This was a triumph of the theory. It explained not only that Kepler's third law held, but also why it held, and what the constant of proportionality meant physically. Furthermore, by applying Newton's laws to more general elliptical orbits, which requires the use of calculus and a more sophisticated analysis, one can show that all three of Kepler's laws follow necessarily from the inverse square law of gravitation. Kepler's first law, that orbits are ellipses, Kepler's second law, that equal areas are swept in equal times, and Kepler's third law, that the square of the period is proportional to the cube of the semi-major axis, are all consequences of Newton's universal law of gravitation combined with Newton's laws of motion. Kepler's second law in particular is a consequence not specifically of the inverse square nature of gravity, but of the more general fact that gravity is a central force, a force that always acts along the line connecting two bodies, which implies the conservation of angular momentum, which in turn implies that the radius vector sweeps out equal areas in equal times. Section 5. Gravitational acceleration at the surface of the Earth. A very important application of Newton's law of universal gravitation is the derivation of the acceleration due to gravity at the surface of the Earth, commonly denoted by the symbol e, and approximately equal to 9.8 meters per second squared, or sometimes approximated as 10 meters per second squared for ease of calculation. Consider an object of mass m resting at or near the surface of the Earth. The Earth has mass m subscript e and radius r subscript e. Applying Newton's law of gravitation, the gravitational force on the object due to the Earth is F equals g times m subscript e times m divided by r subscript e squared. By Newton's second law of motion, force equals mass times acceleration, so m times a equals g times m subscript e times m divided by r subscript e squared, and the mass of the object m cancels from both sides, giving a equals g times m subscript e divided by r subscript e squared. This is the gravitational acceleration at the Earth's surface, which we call g. So g equals g times m subscript e divided by r subscript e squared. This is a very elegant result. It tells us that the acceleration due to gravity at the Earth's surface depends only on the mass of the Earth and the radius of the Earth. It does not depend on the mass of the object being attracted. This is the theoretical basis for the experimental observation, first established by Galileo, that all objects fall at the same rate, regardless of their mass, in the absence of air resistance, using known values. G is approximately 6.674 times 10 to the negative 11 Newton meters squared per kilogram squared. M subscript E is approximately 5.972 times 10 to the 24 kilograms, and R subscript E is approximately 6.371 times 10 to the 6 meters, substituting G equals 6.674 times 10 to the negative 11 times 5.972 times 10 to the 24, divided by the square of 6.371 times 10 to the 6. Carrying out this arithmetic yields a value of approximately 9.81 meters per second squared, which is consistent with the measured value of g at the Earth's surface. This agreement is not a coincidence. It is a verification that Newton's law is correct, and that the model of the Earth as a sphere of known mass and radius is a good approximation. It should be noted that G varies slightly across the surface of the Earth due to several factors. The Earth is not a perfect sphere, but is slightly oblate, meaning it is flattened at the poles and bulging at the equator, which means that the distance from the center of the Earth to the surface is slightly greater at the equator than at the poles. And the Earth's rotation produces a centrifugal effect that slightly reduces the effect of gravitational acceleration, particularly at the equator, and local variations in the density of the Earth's crust can produce small regional variations in G. These effects are small but measurable and are of great importance in fields such as geodesy and geophysical prospecting. Section 6. Gravitational field. It is useful to introduce the concept of the gravitational field, which provides a way of thinking about gravity that is somewhat more modern in its formulation, and that generalizes more naturally to the later and more sophisticated theory of gravity developed by Albert Einstein in the early 20th century, known as general relativity. The gravitational field at a point in space is defined as the gravitational force that would be exerted on a small test mass placed at that point, divided by the mass of that test mass. The gravitational field is a vector quantity with units of newtons per kilogram, or equivalently meters per second squared. If we denote the gravitational field by the vector g, then the vector g at a given point equals the vector force F on a test mass m at that point divided by m. For a single point mass m located at the origin, the gravitational field at a position described by the vector r from the mass is the vector g equals negative g times m divided by r squared times r hat, where r hat is the unit vector pointing away from the mass m, and the negative sign indicates that the field points toward the mass, that is, in the attractive direction. The gravitational field concept is useful because it allows us to characterize the gravitational influence of a mass distribution without reference to any particular test object. Once we know the gravitational field produced by a given configuration of masses, we can immediately determine the force on any other mass placed in that field by multiplying the field by the mass. For a continuous distribution of mass, rather than a collection of discrete point masses, the gravitational field can be found by integrating the contributions from each infinitesimal mass element over the entire distribution. This requires the use of calculus and leads to results that depend on the geometry of the mass distribution. An important result in this context, which Newton himself proved, and the proof of which was one of the reasons Newton needed to develop calculus, is the shell theorem. The shell theorem states two things. First, a uniform spherical shell of mass exerts no net gravitational force on any object located inside the shell. Second, a uniform spherical shell of mass exerts a gravitational force on any object located outside the shell that is identical to the force that would be exerted if all of the shell's mass were concentrated at its center. The second statement is what allows us to treat the Earth, the Sun, and other approximately spherical astronomical bodies as point masses concentrated at their centers when calculating gravitational forces between them and other objects. This enormously simplifies the calculations without introducing significant error, as long as the objects involved are approximately spherical and we are considering distances large compared to the sizes of the objects. The first statement, that a shell exerts no force on an interior object, is also physically interesting. It means that if one were hypothetically inside a spherical shell of uniform mass, one would feel no net gravitational pull from the shell at all, regardless of where inside the shell one was located. This result is specific to the inverse square law, is a mathematical property of the inverse square dependence that makes this exact cancellation possible. Section 7. Gravitational potential energy. In addition to the gravitational force, it is useful to consider the associated gravitational potential energy, which is a scalar quantity that represents the energy stored in the gravitational interaction between two masses. The gravitational potential energy of a system consisting of two masses, 1 and m2, separated by a distance r is U equals negative g times m1 times m2 divided by r. This can be written as U equals negative g m1 m2 over r. Several features of this expression deserve careful attention and are worth dwelling upon. First, the gravitational potential energy is negative. This is a convention chosen so that the gravitational potential energy is zero when the two masses are infinitely far apart. That is, at r equals infinity, U equals zero. As the two masses approach one another, as r decreases, the potential energy becomes more negative, meaning the system loses potential energy. This energy does not disappear, it is converted into kinetic energy, which is why objects speed up as they fall toward one another under gravity. Second, the gravitational potential energy depends on r to the power of negative 1. That is, it is inversely proportional to r, not inversely proportional to r squared, as the force is. This is because the potential energy is the negative of the integral of the force with respect to r, and the integral of r to the negative 2 is negative r to the negative 1. Third, the fact that U is negative and becomes increasingly negative as r decreases means that the gravitational system is a bound system. Energy must be supplied to pull two gravitationally interacting masses apart from each other. This is why planets remain in orbit around the Sun rather than flying off into space. They are gravitationally bound. To escape, an object must be given enough kinetic energy to overcome the negative gravitational potential energy. This leads naturally to the concept of escape velocity, the minimum speed at which an object at the surface of a massive body must travel in order to escape to infinity without additional propulsion, setting the kinetic energy equal to the magnitude of the gravitational potential energy at the surface. 1/2 times m times v escape squared equals g times m divided by r. Cancelling the mass m, 1/2 times v escape squared equals g times m divided by r. Solving for v escape equals the square root of 2gm divided by r. For the Earth, substituting the known values of g, m subscript e, and r subscript e, the escape velocity is approximately 11.2 kilometers per second, or about 11,200 meters per second. This is the speed that a projectile would need to be launched from the surface of the Earth, neglecting air resistance, in order to escape the Earth's gravity entirely and travel away to infinity. Section 8. The inverse square law and its geometric interpretation. The inverse square dependence of Newton's gravitational law, the fact that the force decreases as the square of the distance increases, is not arbitrary. It has a deep geometric interpretation that is worth exploring slowly and carefully. Consider a point source of gravitational influence, a point mass m, surrounded by a series of imaginary concentric spherical surfaces at various distances. At a distance from the mass, the surface area of the surrounding sphere is 4 pi times r squared. The gravitational influence of the mass is distributed over this spherical surface. If we think of the gravitational influence as a kind of flux spreading outward from the mass, and if this flux is conserved, meaning it is neither created nor destroyed as it spreads outward, then the intensity of the flux at any given distance must be the total flux divided by the surface area of the sphere at that distance. Since the surface area grows as r squared, the intensity of the flux decreases as 1 divided by r squared. This is exactly the inverse square law. This geometric argument shows that the inverse square dependence of gravity is directly related to the fact that we live in a three-dimensional space. In a hypothetical universe with 4 spatial dimensions, The surface area of a sphere of radius r would grow as r cubed, and the analogous gravitational force law would be an inverse cube law. In 2 dimensions, the perimeter of a circle grows as r, and the force would be an inverse first power law. The specific mathematical form of Newton's law of gravitation is, in this sense, a consequence of the dimensionality of our physical space. This geometric picture also connects naturally to the concept of Gauss's law for gravity, which is the gravitational analog of Gauss's law in electrostatics. Gauss's law for gravity states that the total gravitational flux through any closed surface is proportional to the total mass enclosed within that surface. This law, which follows directly from the inverse square nature of gravity and is mathematically equivalent to Newton's law of universal gravitation for the relevant class of problems, provides a powerful method for calculating gravitational fields in situations with high symmetry, spherical symmetry, cylindrical symmetry, or planar symmetry. Section 9. Real-world applications. The applications of Newton's law of universal gravitation are extensive and pervasive. They span an enormous range of physical phenomena, from the mundane to the astronomical, and the law continues to provide accurate predictions and descriptions of gravitational phenomena in many contexts, even more than 300 years after it was first formulated. The motion of artificial satellites is governed by Newton's law of gravitation. When engineers and scientists plan the trajectory of a satellite to be placed in orbit around the Earth, or a spacecraft to be sent to another planet, the calculations are based, at their foundation, on the gravitational force law that Newton discovered. The ability to calculate and predict orbits with precision has enabled global positioning systems, weather satellites, telecommunications infrastructure, and the exploration of the solar system. The tides on the Earth's surface, the daily rise and fall of sea levels, are a consequence of the differential gravitational pull of the Moon and, to a lesser extent, the Sun on different parts of the Earth. Because the gravitational force depends on distance, the side of the Earth closest to the Moon is pulled more strongly toward the Moon than the center of the Earth. And the center of the Earth is pulled more strongly than the far side. This differential force, the tidal force, stretches the Earth and its oceans in the direction toward and away from the Moon, producing 2 tidal bulges, and the characteristic twice-daily tidal cycle experienced at most locations on Earth. The orbits of planets, moons, comets, and asteroids within our solar system are all described to an extremely high degree of accuracy by Newton's gravitational law. The only observable deviations from Newtonian predictions in our solar system arise in situations where general relativity must be invoked, most notably in the anomalous precession of the perihelion of Mercury, which was explained by Einstein's general theory of relativity in 1915. For all other planetary orbits, Newton's law provides predictions accurate to many decimal places. The prediction and discovery of the planet Neptune is a particularly striking example of the power of Newton's gravitational theory. By the middle of the 19th century, astronomers had accumulated observational data showing that the orbit of Uranus deviated slightly from the predictions of Newtonian mechanics based on the then known configuration of the solar system. 2 astronomers, Urbain Le Verrier in France and John Couch Adams in England, independently calculated that these deviations could be explained by the gravitational influence of a previously unknown planet at a predicted position in the sky. When astronomers pointed their telescopes at the predicted location in 1846, they found Neptune within 1 degree of the predicted position. This was a profound confirmation of Newton's gravitational theory. The study of stellar systems, binary stars, star clusters, galaxies, also relies heavily on gravitational theory. The masses of distant astronomical objects can be inferred from their gravitational effects on surrounding matter using the same principles Newton established. Section 10. Limitations of Newton's law of universal gravitation. Newton's law of universal gravitation is a profoundly successful scientific theory, but it is not the final word on gravitation. It has known limitations, and these limitations are important to acknowledge. Even in a lecture devoted primarily to Newton's formulation, the most fundamental limitation is that Newton's law is not consistent with the special theory of relativity, which Einstein developed in 1905. Newtonian gravity implies instantaneous action at a distance. If the sun were suddenly to disappear, Newton's law would predict that the Earth would immediately feel the change at the very instant of the sun's disappearance, regardless of the distance between them. Special relativity, however, establishes that no information or causal influence can propagate faster than the speed of light in vacuum. This inconsistency between Newtonian gravity and special relativity pointed to the need for a more fundamental theory. That more fundamental theory is Einstein's general theory of relativity, published in 1915, which describes gravity not as a force between masses, but as a curvature of space-time caused by the presence of mass and energy. General relativity reduces to Newtonian gravity in the limit of weak gravitational fields and slow velocities compared to the speed of light, which is why Newton's law remains so accurate and useful in most practical applications. But for situations involving very strong gravitational fields, very high velocities, or phenomena requiring the highest levels of precision, general relativity is the appropriate theory to use. The anomalous precession of Mercury's perihelion, the gravitational deflection of light by massive objects, gravitational time dilation, gravitational waves, and the description of black holes are all phenomena that require general relativity and cannot be correctly described by Newton's law alone. Nevertheless, Newton's law of universal gravitation remains one of the most important and widely used laws in all of physics. It is accurate, elegant, and powerful, and it continues to serve as the foundational tool for the vast majority of gravitational calculations in science and engineering. It is a law that, despite being more than 300 years old, continues to describe the gravitational universe with remarkable fidelity in the great majority of situations one is likely to encounter. Section 11. Summary and recapitulation. Let us now recapitulate the main points of this lecture, so that the essential content has been encountered more than once, and so that the mind may find in the repetition a gentle and settling familiarity with the material. Newton's law of universal gravitation states that every two masses in the universe attract one another with a force whose magnitude is given by F equals G times M, 1 times M2 divided by R squared, where F is the force, G is the universal gravitational constant approximately equal to 6.674 times 10 to the negative 11 Newton meter squared per kilogram is squared, M1 and M2 are the masses of the two objects, and R is the distance between their centers. The force is always attractive and always acts along the line connecting the two masses. The law was formulated by Isaac Newton and published in the Principia Mathematica in 1687, and it represented the unification of terrestrial and celestial mechanics, the recognition that the same force that makes objects fall to the earth is responsible for the orbital motion of the moon and planets. The universal gravitational constant G was first measured in the laboratory by Henry Cavendish in 1798. Kepler's 3 empirical laws of planetary motion follow as mathematical consequences of Newton's gravitational law, combined with Newton's laws of motion. The gravitational acceleration at the surface of a spherical body of mass m and radius r is given by g equals g times m divided by r squared. The escape velocity from the surface of a body of mass m and radius r is v escape equals the square root of 2 gm divided by r. The gravitational potential energy of a two-body system with masses m1 and m2 separated by distance r is u equals negative gm1 m2 divided by r. The inverse square dependence of the law has a geometric origin related to the three-dimensional nature of space. Newton's law has important limitations and is superseded by Einstein's general theory of relativity in regimes of strong gravity and high velocity, but remains accurate and indispensable for the vast majority of practical applications. All of these things have been stated before in the course of this lecture, and they are now stated again, so that they may be heard once more, and so that the ideas may be encountered a final time before the mind settles into the quiet that follows careful and attentive study. This concludes tonight's lecture on Newton's law of universal gravitation. Please review your notes